Okay, so this video is meant to introduce you to the idea of momentum. And momentum is kind of a hard idea, topic to kind of quantify. Essentially, momentum is the product of an object's inertia and its velocity. So something can have a really large momentum because it has a really big mass. So like a football player that's running on the field, or something can have a big momentum because it has a really big velocity, like a bullet. Something to note is that it is a vector quantity, so it does have a magnitude and a direction. So we're going to have to keep that in mind. We're going to have x momentums and y momentums. The symbol for momentum is a lowercase p. I know, it doesn't make sense. You just have to get used to it. The equation is going to come right out of the definition. Momentum is equal to mass times velocity. And if we think about the units for momentum, mass is measured in kilograms, and velocity is measured in meters per second. So there's nothing that equals that. Like, it's not like how a joule was kilogram meters per second squared, and that equaled this new quantity equals a joule. Momentum doesn't have a new quantity, it's just kilograms and meters per second. Again, a little strange, you can just deal with it. So momentum by itself is pretty straightforward. Another quantity that we're going to look at is called impulse. And impulse is a change in an object's momentum. And there's a couple different ways to kind of think about impulse. And it's a change in an object's momentum due to a force. And that arises from the fact that we're not looking at changing the object's mass, but we're looking at changing the object's velocity. So if momentum is mass times velocity, an impulse comes from the fact that we change the velocity. And whenever we change the velocity, we call that an acceleration, and the causes of acceleration are forces. So if we look at Newton's second law, a little bit of a revisit here. Newton's second law says that the net force on an object is equal to mass times acceleration. And if I were to put in the equation for acceleration, acceleration is a change in velocity over change in time. So if I were to say the net force is equal to mass times my change in velocity over change in time. And if I brought the time over, and I'm just going to write this as F net. If I multiply time by both sides, so F net times delta T is equal to M times delta V. Here essentially we have impulse, because impulse is a change in momentum that is causing the object's velocity to change. So there's actually two equations for impulse. Yes, here, let me write what the symbol is. The symbol for impulse, you ready for it? It's going to make a lot of sense. A capital J. And the two equations for impulse are that impulse can equal force times delta T, and this time is specific. It's called an impact time. It's the time over which that force is being exerted. So that is one equation that we can solve for impulse, and the other we can solve for it is just a change in momentum. And again, it's a change in momentum, so the units are still going to be kilograms meters per second. So one of the most common examples of impulse and like combining these two equations is looking at airbags. So if we looked at a car with airbags versus a car without airbags, impulse really helps us understand what's happening in terms of the damage that can arise. So I have two scenarios. One scenario is, here's my car, it's 1,000 kilograms, it's traveling at 5 meters per second, and it hits a wall, and it kind of becomes mangled, and its final velocity is definitely 0. And then I have a situation where I have no airbag, and I have a car that has a mass of 1,000 kilograms, it has a velocity of 5 meters per second, it hits a wall, and again it comes to rest. So we're going to compare these two and look at what's happening in terms of momentum, what's happening in terms of forces. So if I looked at the initial momentum of this car, my change in momentum is mv final minus mv initial. Well, my MV final is just zero. Like I come to a complete stop. So my change in momentum essentially would be the mass of this car, so I've got a minus there, 1,000 times my initial velocity of 5, so that's going to be negative 5,000 kilogram meters per second. So if I have an airbag, the change in momentum that the car is going to experience is going to be negative 5,000 kilogram meters per second. Let's look at it if I don't have an airbag. So if I don't have an airbag, again I look at my momentum equation. MV final minus MV initial. My final velocity is still 0, so that's going to become 0. And if I calculate it out, that's going to be negative. My mass is 1,000. My initial velocity is 5. I'm still going to have negative 5,000 kilogram meters per second. So whether or not you have an airbag, your change in momentum is still going to be the same. What is going to be different is the force and the time of impact. See, when you have an airbag in your car and there's a sensor in your car that all of a sudden detects that there's some kind of a collision and there's some kind of force, the airbags immediately deploy. They're huge. And your face hits the airbag. But it's not like this big inflated ball that you run into, because then you just bounce off of the airbag. The airbag immediately inflates and then it has the ability to deflate. So what it does is instead of your face hitting the steering wheel in a split second, it takes like a good solid second for your face to like go into the airbag and come to a velocity of 0. So the impact time with an airbag is going to be something like, let's say my impact time, my delta t is like 1 second, whereas if I don't have an airbag, my delta t is like only 0.1 second. Okay? The airbag, what it does is it increases the impact time. Now let's look at what happens to the force. Because there's another equation for impulse. Remember, impulse is also equal, my delta p can also be equal to force times delta t. This is my other equation for impulse. So I already know my delta p is negative 5,000, so negative 5,000 is equal to my force times 1 second. This would give me a force of negative 5,000 newtons. So I'd have 5,000 newtons coming at my face. That doesn't feel very good. Maybe you get a broken nose. In this case, my negative 5,000, my force, or my change momentum, my negative 5,000, so my force times 0.1 second. In this case, my force is going to be negative 50,000 newtons. Much bigger force. It's going to cause a lot more damage. And so we see this with airbags, but we also see this with just other examples of impulse and how if we increase the impact time, then we're going to decrease the force. So classic example is like a water balloon toss. Like if someone's going to throw you a water balloon, you don't stand there with your hands out and your elbows locked, just catch it on impact. It'll break. You cradle it. And what you're doing in that sense is the moment that the water balloon touches your hand, if it's like an egg toss, the moment it touches your hand, that's where the impact time starts. So the impact time starts, the impact time ends. And so you increase the impact time, and if you increase this number, the force is going to decrease. The same can be said with like if you had an egg that dropped on grass versus an egg that dropped on concrete. With grass, there's more give, and the little like grass blades are gonna, fall down. You're gonna have more impact time. And there's other things within a car that increase the impact time, like that increase the time over which it takes for like basically your body to come to a velocity of 0. Your steering column collapses. Your seat belts are like braided nylon to kind of give, so it's not this immediate impact. But the key to impulse and understanding this is that the change momentum is the same. Whether I had an airbag or no airbag, I still have 5,000 for my impulse. What changed was my force and my time. If my time goes up, my force goes down. So now we're going to transition and do some example problems that are going to practice impulse.